And what I'm going to do in this video is essentially very simple. I'm going to calculate the electric field at the axial point of a charged disk. And to do this, I'll need the electric field on the axial point of a charged ring. So let's begin. I'll assume that the charge distribution is uniform. So let's begin. Here is my ring. Name the point P. Let the center of the ring be C. The distance between C and P is x. So we have to find the electric field at an axial point of a charged ring, a uniformly charged ring, a distance x away from the center C. To do that, first of all, we pick a small element which has a very small length, therefore it has a very small charge dq. The electric field that this segment will produce at point P will have a direction like so. Let's call this angle theta. Then this angle is also theta. These two angles are vertically opposite. If I choose a diametrically opposite element of the same length, of the same small length, by small here I mean infinitesimal. This element is almost a point because the length is very small. It's infinitesimally small. The charge carried by this portion will be the same as the charge carried by this portion. Therefore, this portion will also have a charge dq. The electric field at point P due to this segment will have the same magnitude dE but directed like so. By symmetry, this angle will also be theta. First off, we have to calculate the net electric field at point P. If we resolve these small electric fields dE, well, why are these electric fields small? Because the charges that create these electric fields are small. If we resolve these electric fields, the vertical components, d sine thetas, they will cancel out. And we will be left with the horizontal components, which we can call dE cos theta. Well, why don't I write 2 dE cos theta? Because eventually, to find the net electric field, I'm going to have to integrate. I'm going to have to integrate dE cos theta. And integration is basically addition. It's addition of many things. It's addition of an infinite number of things. So, because I'm having to integrate dE cos theta, I don't need to write 2 dE cos theta. Because I'm integrating the horizontal components of the electric fields due to all segments coming from different parts of the circumference of the ring. Well, what's dE? For that, we just use Coulomb's law. It's 1 divided by 4 pi epsilon 0 divided by charge. Well, dE electric field is created by small charge dq divided by the square of the distance between the point and the charge. In this case, it's just square root of r squared plus x squared from Pythagoras' theorem. This triangle is of course a right angled triangle. So the square of this distance will simply be r squared plus x squared, and then we need cos theta. Well, cos theta from this right angled triangle is just base divided by hypotenuse. The base is x, the hypotenuse is square root of r squared plus x squared, which makes the denominator here r squared plus x squared to the power of 3 by 2. Now first of all, to integrate this, we take all the constants out. You should realize that this distance, it's a constant. Why is it constant? Well, because if I join all the points on the circumference of the ring to the point P, all points from the circumference of the ring to the point P, what I'll get is a cone. And this will become the slant height of the cone. And the slant height of the cone is the same everywhere. Another way in which you can think, is that r is constant, x is constant. Whichever point of the circumference of the ring I may be on, r and x are always constant. Therefore, square root of r squared plus x squared is also a constant. So if I take out all the constants, I'm left with 1 by 4 pi epsilon 0 x divided by r squared plus x squared all to the power of 3 by 2. What remains is integration of dq. I've taken all the constants out. What remains is integration of dq. Now what is integration of dq? It's just the total charge q plus capital Q. Why is it so? Well, integration dq means that I'm adding up all the small charges from the circumference of the ring. If I add up all the small charges coming from the circumference of the ring, obviously I get the total charge of the ring, which is q. So let me just write it as q here. So now I know the electric field at an axial point of a charged ring, a uniformly charged ring. All I'll need now is this formula. I can erase the rest. So let me erase the rest. What we had originally set out to do is to find the electric field at the axial point of a charged disk. So let's draw a disk, and let's say that the total charge that this disk carries is plus capital Q. It is distributed, this charge plus capital Q is distributed uniformly throughout the area of this disk, and therefore we can introduce a quantity called surface charge density. And surface charge density, in this case it's constant because the charge distribution is uniform, is Q divided by pi r squared, r being the radius of the disk and pi r squared is the area of the disk, just the area of a circle. And we have to calculate the electric field at this point P, which is again a distance x away from the center of the disk along the axis of the disk. Of course, things will get a little more complicated if the charge distribution was non-uniform. In that case, when we integrate, we won't be able to take out the charge density from the integration. It won't be a constant. But we'll deal with that some other time. To calculate the electric field at this point due to this entire disk, we imagine that the disk is made up of many concentric rings. Each ring has a very small thickness, an infinitesimal thickness. And if we can calculate the electric field due to one of those rings at this point, then we can use the technique of integration to calculate the electric field at this point due to the entire disk, imagining this disk to be made up of many infinitesimally thick concentric rings. So you can imagine this disk to be filled up with many concentric rings until you start over here and you go on creating those concentric rings until you reach the edge of the disk. So let us imagine one of those rings. I'll draw the ring over here so as not to mess up this diagram. Let's imagine that ring to have a radius A and a thickness dA. It has a radius A and a thickness dA. So to find out the electric field at this point due to this ring, which is actually somewhere over here, I'm drawing it over here because I don't want to mess up this diagram, and well, I could have used different colors, but at this moment I'm out of colors. I only have black. To calculate the electric field at this point due to one of those concentric rings, I can use this formula. Well, in that case, I'm just rewriting this formula, but for this ring. The electric field that this ring will create at this point will obviously be a small electric field, dE, because the charge that this ring carries, well, where does that charge reside? That charge resides in this infinitesimally small thickness. Because the thickness is very small and the charge this ring carries is spread over this thickness, the charge that it carries is very small, and therefore the electric field this infinitesimally thin ring will create will also be very small. Just simply rewriting this formula, the constant that I get is 1 by 4 pi epsilon naught. Well, x is just x, it's this distance. Q becomes dq, it's small charge, divided by r squared plus x squared to the power 3 by 2. Now if you remember, in case of that ring, r was the radius of that ring. In this case, the ring I am talking about has a radius a. So the denominator becomes a squared plus x squared to the power of 3 by 2. What is dq? dq is the charge carried by this infinitesimally thin ring. Well, what is that charge? It is the surface charge density, or the charge per unit area, which is uniform, which is constant, multiplied by the area of this shaded region, which is the area of the infinitesimally thin ring. How much is that? The area of the ring is 2 pi a dA. How do I arrive at this formula, 2 pi a dA, for the area of the infinitesimally thin ring? Well, there are many ways to think about this, many ways to figure it out. One especially simple way is to imagine that you cut this part out and straighten out the circle. If you straighten out the circle, the shaded region will become something like so, and the circumference will become the length. The thickness will become the breadth, and the rectangle has area 2 pi a times dA. So the charge carried by this infinitesimally thin ring is this quantity, sigma times 2 pi a times dA. So in place of dq, we can simply substitute this expression, sigma times 2 pi a times dA. So sigma times 2 pi a times dA. Let's make it bigger. The pi's cancel out, of course. 2 cancels 4 and we get a 2 in the denominator. What we are basically left with is this. Well, eventually we are going to integrate this, so we better write it in a form that makes it slightly more simplified. So we take all the constants out. We write down the constants first. Sigma is a constant, x is a constant, they are of course in the numerator, 2 epsilon naught comes in the denominator. A is not a constant, and this part of the denominator is also not a constant. A squared plus x squared to the power of 3 by 2 is not a constant. Why isn't it a constant? Well, because I am imagining that the disk is made up of many infinitesimally thin concentric rings which start out over at the center and eventually take up the entire space and end here at the edge. A of course varies. A starts from 0 and goes up to r. A changes from 0 to r. So to find the net electric field, I'll have to integrate this quantity. This part is constant, so I'll just have to integrate this quantity. The limits of integration will obviously be from 0 to r. Why are the limits as they are? Because I'm imagining the disk to be made up of many infinitesimally thin concentric rings which start out at the center and end at the edge. Therefore, the radius of the rings that I'm talking about start out at 0, therefore A begins at 0 and ends at R, right at the edge of the disk. This is a simple integration. You can do it using integration by substitution. I don't remember the formula for this. In fact, I remember very few formulas. I prefer to do everything from first principles. So let's just work it out. I'll work it out over here. ADA divided by a squared plus x squared to the power of 3 by 2. The whole thing has to be integrated. Let's bring a half here and a 2 here. Let's assume that a squared plus x squared is t. If I differentiate both sides, x is of course a constant. Differentiating x squared will only yield 0. So I get a 2ada equals dt. X squared is a constant and its derivative is 0. So 2ada is dt. In the place of this I can substitute dt. So let me write it out over here. Half integration dt divided by this quantity is t. So divided by t to the power 3 by 2, which can be written as t to the power of minus 3 by 2. What will this integration give me? This integration will give me half t to the power of minus half divided by minus half. I'm just using a very simple formula. Integration x to the power n dx is x to the power n plus 1 divided by n plus 1. So using that formula, integration x to the power n dx gives x to the power n plus 1 divided by n plus 1. I end up here. The 2's cancel out. So this is minus 1 divided by square root of t. But t is this quantity is t. So I can simply write square root of a squared plus x squared. So the indefinite part of this integration is this. We'll put in the limits slightly later. Let me just write this x a little more clearly. I no longer need this formula, so I'm erasing it. So what are we left with? E equals to sigma x by pi epsilon 0 minus 1 over square root of a squared plus x squared, and the limits, the lower limit is 0, the upper limit is r. I think I should erase this also because I don't have too much space to work with. I'm erasing this. I hope I wrote it down correctly. Yeah. So let us just put in the limits. If we put in the limits, the upper limit first. Remember, the variable is a, not x. This is of course not standard very much. The standard thing to do is to take x as your variable. A's are usually constants. A's, B's, alphas, betas, gammas, they are usually constants, whereas x and y is their variables. But we started out with somewhat of a quirk, and here we are with x to be our constant and a to be our variable. So first of all, we put in r in place of a, the upper limit, which gives us minus 1 over square root r squared plus x squared. If we put in the lower limit 0 in place of a, we are left with 1 over x. So this is the expression for the electric field at the axial point of a uniformly charged disk. This could have been done in other ways, in many different ways. I chose a way that is especially simple. Although it is a bit lengthy, it's simple. There are other ways which makes the entire derivation very short. Gauss's law is one way. Of course, using Gauss's law, we can only find the electric field due to an infinitely large disk. If the disk is infinitely large, We can even get to the result that Gauss's law gives starting from here. If the disk is infinitely large, which means r goes to infinity, it means r is very large. What do we get? Well, the electric field due to an infinitely large disk or any infinitely large surface, because if the surface is infinitely large, it doesn't matter whether it's a disk or a plane or anything else. Sigma over 2 epsilon 0. Let's take the x in. If we take the x in, well, we get a 1 from here. X divided by x is 1. X divided by square root of r squared plus x squared. I hope you understand what I did. I wrote this thing first and this thing later. In this part of the expression, let's divide numerator and denominator both by x. If I divide the numerator by x by x gives 1, and I'm dividing the denominator by x, so inside the square root I'm dividing by x squared, so I get r squared over x squared plus x squared over x squared, which gives me 1. Now if r is infinite, this expression becomes 0. This is simply 1 over infinity. Infinity squared over x squared is simply infinity. Infinity plus 1 is infinity. So in whichever way you look at it, this thing becomes 0, and the electric field due to an infinitely large surface is simply sigma divided by 2 epsilon 0. This is one way to check that this formula that I had arrived at by integrating was correct, because this matches with the result that we get from Gauss's law. We could have arrived at this result or this result by doing the problem in ways that were different, that would have been different from the way I did it, or different from Gauss's law. But there you have it. This is just one way. In physics, usually we can solve a problem in multiple ways. This is just one simple, straightforward, very direct way to do this problem. Thank you.